Today we'll continue our foray into matching, and and we will complete our algorithm from last time. Most likely we'll see another interesting algorithm today for matching, hopefully, and then we will move to our promised parameterized streaming algorithms. Okay, so recall last time what we were trying to do. So we came up with this interesting algorithm, which was a very generic algorithm. Okay, so let's recap a little bit, and then we will go back to whatever we proved last time. So recap was that what we did is that suppose we wanted to solve some problem, like weighted problem and approximation, then we started with our objects. In our case, this was matching, so these were S's. Okay, and we started with a weight function, W1. Then we found some local structure, and what was a property of that local structure is that any optimum solution has say any optimum solution intersection local structure, say intersection local structure has weight at least L, and essentially we showed that any feasible solution or any minimal feasible solution has alpha times L locally. Okay, so this is how we went around, and essentially how did we get from W1 to another weight function? It was essentially the same weight function, except at some coordinates we subtracted the same quantity. Okay, and what is the subtracted the same quantity? We actually subtracted any optimum solution, say at least L. Okay, so we basically subtracted minus L from here, the guarantee which we were given to us. And then we further went down, okay, found some local structure. Okay, maybe let's say L1, and then maybe somewhere we do minus L2, okay, so on and so forth, until we reached a point where, and this decomposition was the fact that all the time we find a positive edge or object and use that as a fulcrum to decompose our weight. Okay, and this is the way we reached, say, some Wm last point. Okay, where everything was, say, less than equal to 0 weight. Okay, so this is how we reached this. So one way to think of this local ratio algorithm is also an induction, right? Inductively, if I have found the solution up until here, how can I extend a solution from here to here, right, with the solution here, and still preserving the fact that at every step of my iteration or every step of my induction, the solution what I have is an alpha approximation with respect to my current weight function. That is all that I was trying to do. Okay, so here in our case, because we were talking about maximum matching or any weighted problem, an empty set was a solution, and inductively we try to say, look, if at any stage, if this object is not my solution, then like with respect to my say, so when I went from, say, W3 to W3, I had a solution, and I tried to go through W3 to W2, then I noticed that, well, I can write W2 as something as W3 plus W3 bar, and whatever my solution is, either that or some modification of that is simultaneously an alpha approximation for this and simultaneously alpha approximation for this. And with help of this, we argued that that is also an alpha approximation for W2. So inductively, we had this invariant that after each step, we are able to preserve the fact that whatever solution we have, or we are carrying a solution that is in fact alpha approximation with respect to my current weight function. Okay, so and local ratio, or the technique of local ratio was used here to say that, look, the small object we have found that guarantees me that when I go back a little bit, I have to pay some, and the approximation solution that I can compute or I can make is not too much more, but I can pay alpha times this local guarantee and obtain a solution to this, to my current weight function, which is an alpha approximation. Okay, so this was the basic idea or basic tool which we tried to do this. Okay, now then we try to specialize this argument with respect to matching. And that is where we realize that the way we are making this decomposition, weight decomposition, if you recall correctly, is that this is how our weight function was. So we started with W1, we found a structure here, and we said that, look, at this point of time, let me find an edge whose weight is non-zero. Okay, and notice that when I'm down the line trying to traverse these things, if I know the current weight function completely, then whether this edge has weight greater than 0 or not is a very simple object to do. But if this is implicitly given to me, then I need some methodology or machinery to compute whether the weight of a current edge is greater than 0 or not. So we found such an edge, and so that was first operation, was given this edge, what is his weight? If it is non-zero, then the operation we defined is that get a new weight function where you decrease this particular weight from this edge and all its neighbors. So this is the operation we defined. And then we noticed that, well, if I want to do this in streaming, neither do I have this whole weight function, or neither I have these edges which needs to know this. But all we saw in the algorithm, so then we converted this algorithm into this potential based algorithm, which for every vertex stores the following set of information. It tells me all the edges which were initially, which up until now in my stream is incident to me, and they are present in the stack. And because of that, what is the amount of weight do I subtract from my current weight? So this is what we stored in this potential, if you recall correctly, right? This potential, right, is the total sum of the weight already reduced from the edges incident to the vertex V. Okay, and that has already come before. So this was a potential. This was the potential function we defined, and based on that potential function, we defined the following algorithm. Okay, so let's go through this algorithm. So we had a stack S. For each vertex V, we had this potential phi V, which was initialized to 0. Now, when any edge UV comes, I check if the weight of E is less than phi U plus phi V. If it is not, you move to the next edge. Otherwise, I push this edge to the stack and I make some modification. What is the modification do I need to do? Okay, so the modification that I needed to do was that what is my current weight? So my current weight is W prime E is WE minus phi U plus phi V. This is my current weight. Okay, or yeah, current weight if I would have reduced this. Then I need for the future edges to remember the fact that on U and V, edge E has come, and because of that, we need to subtract the quantity W prime E from any future edge which is incident on U, or any future edge which is incident on V. So we noted that by noting to phi U, adding this W prime E, same with phi V, adding this. And how do we get an algorithm? We unwind the stack and create the matching M greedily in the stack order. What do we mean by this? The last item which has gone into the stack, I start this, and then you pop the remaining items. And if you can greedily add the current edge to my matching, you add, otherwise you move forward. Okay. So this is the stage which we set up everything. Now we wanted to say that, look, by doing this, it is indeed a good approximation algorithm. Okay. So let M star be the maximum weight matching, and let M be the matching returned by our algorithm. Okay. Now suppose this is the order in which edges are coming, E1, E2, dot, 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 EM. And what is MI? MI is M intersection EI to EM. Okay. Now I defined a weight function. What is the weight function? Look, so weight function is weight of EI is weight of E minus phi of U minus phi of V, where phi I are the potential values just before the ith edge in the stream has arrived. Okay, so suppose E has arrived now. Okay, so at this point of time, what is the value of U and what is the value of V? Okay, so this is what Wi of particular edge is. Okay, so look at their endpoint, its current weight or its real weight minus the potential which is stored at U and V. Okay, and then we try to understand how a weight function Wi and how a weight function Wi plus 1 of new edge are related to each other. So this is where we were trying to understand everything. Okay, so let's go back here. Okay, so suppose I have a current weight function Wi, and let's try to understand what changes Wi and Wi plus 1 would have. So here is my weight function I. So recall, so how is the defined? Weight function of I of E is phi U, weight of E minus phi of U plus phi of V, right? This is all that we have. Okay, and okay, so now let's look at Wi plus 1. Okay, this is my Wi plus 1. Okay, I ask myself, so what is happening? So now EI, so this was phi value of, so I should be writing phi I, okay, of U and phi I of V. Now let's look at how the potentials are changing, okay, at phi I plus 1, okay, so on and so forth. Now notice by the way we are doing something, how does the potential changes? Right? How does the potential change it? So what we did to the potential is that after this stage, we made an update to potential. Suppose EI is U comma V. What potential did you make change to? You added the value, this particular value. Okay. So basically, phi I plus 1 of U is phi I of U plus Wi of E, right? Similarly, phi I plus V is equal to phi I of V plus Wi of E. Rest phi's remains same, right? Remains the same. So now I ask myself a following question. Okay, now what changes Wi plus 1 does to an edge, some say E tilde? Okay, here's my edge E tilde. What change Wi plus 1 have? What change Wi plus 1 will have on E tilde? Okay, so now we have several cases, right? Suppose E tilde is U tilde and V tilde. U tilde, V tilde is not an element of U comma V. Okay, then their phi's have not changed at all, right? So in that case, okay, so their phi's have not changed at all. So in this case, weight of E tilde, since what is this? It is weight of E minus phi I plus 1 of U tilde plus phi I plus 1 of V tilde, right? But this is same. So this is weight of E minus phi I of U tilde plus phi I of V tilde, which is weight of E minus, what is this? Okay, so this is same as what I'm saying. Okay, this is same as weight I of E tilde, which is, this is what we did, this is what we expect. But notice, if I have this E tilde is this, and suppose one endpoint is U. Now, what will then happen? If you notice, if this happens, then if I go write down Wi plus 1 of E tilde, then it is weight of E. But now, suppose U tilde is U. Okay. Now I know that my potential of U tilde, U had changed. By how much? By this quantity Wi of E, right? So now what will happen is that or look at this way. Now, this is the weight function after I have done this edge modification. It means all the edges which were incident to UV now will lose its current weight by W change which we have added, which means you can do computation also here, but this will lead to, what is this? So it is W, it is nothing but, okay, whatever may be the weight of I, weight of this was my weight in the ith stage. Now please even subtract further, how much? I have subtracted this quantity. Okay, so this is going to be weight of I EI. Okay, so this is what will be your weight function, or the relation between weight I and weight I plus 1. Okay, now what happens for the edge UV, right? Well, weight I plus 1 of EI is weight of I of E, but now notice I have also reduced the potential of U by this quantity. I have also reduced the potential of V by this quantity, or in other sense, when I look at this edge, it will drop by this quantity. Okay, so this is a relation between weight I plus 1 and weight I, which is basically what is this is that, look, if EI went into my stack, it initiates certain decrement operation on the weight function of the edges which are in its neighborhood. Okay, and so including himself, so all other edges but himself, it subtracts Wi, like it's a magnitude by which it should drop, so it drops. And for EI, well, it should have just dropped by itself WIEI, but we don't do that, we just subtract by 2. Okay, so that's the only difference. Now let's ask ourselves, so this is just how the weight functions are. So now I'd like to, as I told you, right, we could directly apply local search and say, but let's see if this is how we thought of this algorithm as some sort of inductive way of algorithm, then what can we do? So I'm going to show to you, this is what I'm going to show to you. This is what I said. So for all I, weight I m star is less than equal to 2 times weight I of mi for all I, and I'm going to have induction on decreasing I, right? So why am I doing induction on decreasing I? Because W1 or W1 is a weight function before I have not seen any edge, right? And what is our goal? our goal is to show that W1, which is, or W1 of M star is less than equal to 2 times W1 of M, right? This is what my ultimate goal is. But to show this, I'm saying, look, let's do in a decreasing way. So suppose I have E1, E2, EM. This is what it came. So look at the last weight function, Wm. Okay, M. So what is a Wm? Wm is a weight function just before EM has come, because W1 is a weight function before E1 has come. So Wm is the weight function just before EM has arrived. Okay. What can we say about Wm? So this is a function from edge of this graph to some reals. Okay. So what is Wm of E? Anybody? If E is not equal to Em, can we say anything?
It's negative.
It's negative, correct. So for every edge, the weight of this, so we can say, okay, this is your, okay, so this is less than equal to 0, this, okay. So this is a property of this. Okay, great. Okay. Now, so I have to, so I'm trying, so this is my base case, okay? This is my base case, which I'm trying to handle first. Okay. So let's think of this way. Let's say, okay, so let's do a slightly more cleanly, okay? Now let's say Wm of Em is, say, less than equal to 0 and greater than 0. Okay. Now, if weight of M is also less than equal to 0, right? Then what do we know? Em is not part of the stack. That's one thing. You did not add Em to the stack. That's one thing. Now, MM could either be empty set, okay, or, I mean, in this case, what is MM? Is like either it could be empty set or MM could be, I mean, what is MM? Do you recall what MM was? MM was intersection of the matching which we returned, okay, to, so recall, MI was my matching which I returned with EI to EM. So what will be MM is nothing but my matching intersection with EM. Okay. So now, okay, now let's just do this case first. This is slightly easier, even if this is easy. Now, what can you say if weight of EM is greater than 0? First of all, EM is in a stack. And what is MM? Recall, M intersection EM. This is equal to? I claim this is equal to EM. Do you see why? Recall, how are you making your algorithm, matching algorithm? You go greedily in the stack order, right? So whichever the last element which has been put inside the stack, that is part of every matching you took. right? You will take that element because you start from that edge, because at that point of time you have an empty matching, right? So none of the edge endpoint of this first edge is part of anything, so you will pick this up. Okay, now, well, I don't know, maybe. So now if you look at M star, Wm of M star, either it contains Em or it doesn't contain Em. If it contains Em, well and good. Okay, if it contains Em, it is well and good, or it doesn't contain Em. If it contains Em, then I know my mm also contains Em. So this is also less than equal to 2 times Wm of mm, and then we are good. Okay, in either case, whether M star contains Em or M star doesn't contain Em, but I know my mm contains Em, and hence I'm very good. Okay, but here I know that all the weights are what do you call negative. So if this is less than or equal to 0, mm is not part of the stack. So mm is always empty here, right? Because this is not part of the stack. So how can my matching can even contain this edge? Okay, but in this case, this we are perfectly fine because weight of mm star, okay, this is some quantity which is less than 0 because every edge here is 0, because we just now argued that every edge was less than or equal to 0, and weight of em is also less than or equal to 0 in this case. So weight of mm star is less than or equal to 0, which is less than or equal to 2 times weight of mm, because at least this is 0. Agreed? Right? So base case is all good and done. Okay, so now let's do induction hypothesis. Okay, so what do we know by induction hypothesis? That weight I plus 1 of m star. Notice one thing, m star, your maximum matching, I'm not taking anything. So I'm believe it's just that the weight functions are changing, not m star is not changing, right? But though my mi's are changing, it's just an intersection of this set of edges. But m star is not changing. So this is how you should think about these kind of algorithms. Okay, so this is less than or equal to twice weight I plus 1 mi plus 1. Okay. Now, suppose if EI is not in the stack, okay, then what we know, then we know that WI is equal to WI plus 1. Okay, then this is simple. WI of M star is less than is equal to, yeah, so WI of M star is equal to WI plus 1 of M star, which by induction hypothesis is less than or equal to 2I plus 1, okay, which is less than or equal to 2 times, or this is rather equal to WI MI plus 1, okay. But MI plus 1, because EI does not belong to the stack, MI plus 1 and MI are exactly the same thing. So this is 2 times weight of MI. So we are happy. Okay. So this is in the case when EI is not in S. So now let's look at the case when if EI does belong to S. Okay. And let N be the set of edges intersecting EI in G. Okay? Then what can we say? Let N be the set of edges intersecting EI in G. Okay? Then I claim, look at your weight I of M star. Okay? Plus 2 times WI EI. Why? Look, here is your EI. And these are the set of edges of N. Any M star can intersect how many edges from this? Just 2 edges. Maybe this and this. And what is the change? Look, with respect to EI, I know that when in Wi plus 1, I subtracted from each of these edges exactly weight IEI. This is all that I did. I subtracted this. Right? Look, it could also be that it's just EI. If like M star contains just EI, right? If it just contains EI, so remember in Wi plus 1, we decrease this weight of this edge by exactly 2 times WI-EI. So either you contain 2 edges, or you contain exactly 1 edge, in which case it is EI, or in either case, weight of Mi star, whatever your weight in M star, and twice the weight of ith weight of this EI. This is all that it is. Okay, which implies this is equal to, now by induction hypothesis, what is this? This is less than equal to 2 times Wi plus 1 M star plus 2 times WI-EI. Okay. Now this is an upper bound. Okay. Now I'm going to show a lower bound on Wi M star. Okay. So look at Wi M star. Okay. Can M star not contain any edge from N? Is it possible that M star doesn't contain any edge from N?
No, it is not possible.
Right? Because you have a positive weight edge EI, right? Which immediately implies that this is at least equal to Wi plus 1 of what I'm saying. Okay. Not even M star. I'm sorry. Mi. Forget about M star. All we need is Mi. So look at Mi. Mi, I was creating this matching, right? So it must be containing, look, not containing, because I was creating this Mi greedily. So when I create this Mi greedily, and if I can, why did I not add edge EI? Because there was some edges incident to which were added, because EI is part of the stack. Okay. So either way, so weight of Mi is weight I plus 1 of okay, let's see. Okay, fine. Which is greater than equal to, is this fine? Look, weight of Mi is at least this much, right? Like just Mi. But look, Mi plus 1 contains less edges than Mi. Could contain less edges than Mi, because it's a intersection from EI plus 1 to EM. And what is Mi? It's an intersection from EI to EM. So what does this give us? Is this fine? Okay.
Sorry, I do not see the last inequality, because Mi plus 1 can include a EI.
No, Mi can. Mi can.
Wait.
Mi can. Piotr. But Mi plus 1 is a smaller set than Mi, right?
Yeah, but sorry, it can contain edge incident to M.
No. So look.
Oh no. Okay. Sorry. Yeah. Sorry.
Like Mi is a superset of Mi plus 1. Because what was Mi? Mi is a M intersection EI to EM. Mi plus 1 is a M intersection EI plus 1 to EM. So this weight can only be smaller. Okay. plus this. But now we are done, right? Right? Look, weight I of M star is at least this much, right? But we know that weight of Mi is at least this much. So what does this imply? I claim, look at weight of Mi star. Okay, what is weight of Mi star? Right? Is less than equal to 2 times Wi Mi. Right? Because look at this quantity. Okay. Okay, so if this is not clear, let's see. What did we wrote here? Let's see this here. Okay, this is from here, I'm saying weight I of M star is less than equal to 2 times Wi plus 1 M star plus 2 times Wi EI, which is less than equal to, if I take Wi plus 1 M star plus Wi EI, right? Now, this quantity is less than Wi Mi. So this is less than equal to 2 times Wi Mi. And this is exactly what we wanted to show. Okay, as required. So even using induction, we can prove these things. Okay, so what we managed to show up until now, that our algorithm is a factor 2 approximation. Okay, but if I go back in the algorithm, right? So there is one issue in the algorithm that which I did not handle at all, is that in this algorithm, now we know that it is space efficient and it's a factor 2 approximation, except that I don't have any guarantee that how many edges we are going to put inside the stack. Do you understand my difficulty? Okay, so let's cut this algorithm. Okay, so this is the algorithm we had. Okay, now we need to do some modification to this algorithm to handle the case. So all we managed to show is that this is a factor 2 approximation. Okay, and and we can manage to do all the operation of all the operations inside this in order n log n space, but we have no guarantee over stack size. Okay, so what do you think we should go and do? Okay, so I'm just going to go slightly slightly differently. Okay, and let me write down something: primal and dual. Okay, so max summation E in E, weight E, XE, this is matching. And for all V in V, summation V belongs to edge is XE is less than equal. So for every edge, I have a variable, and for every E in edges, XE is greater than 0. So what is its dual LP? Its dual LP is a minimization, and you know very well, summation V in V, YV, for all U comma V in E, YU plus YV should be greater than equal to, suppose This is E, right? And for all V in V, YV is greater than 0. So what is this? Do you know what is this? Dual? Anybody?
Well, yes, but maybe not everyone.
So do you know that this is, look, if you do, look, it is just to give you intuition from where we will get the ideas, okay? But if you do not understand this, it is perfectly valid. So this is a matching linear programming, and it's a dual, so it's a vertex cover LP. This is basically a vertex cover LP, right? So what is this? So for every vertex, I have a variable, okay? So, and I want to minimize the weight. I want to minimize the, so I want to minimize this, this such that for every edge, UI, U plus UV, the value of this U, so this is not a 0, 1 variable. So like, think of this is like a weighted variable, okay? And UI, U plus UV is at least WE, okay? Now, for all V in V, UV is greater than 0. So this is basically a vertex cover in the sense that, if I would have put 1, then it is much more clear this is this. But I have weights on edges, and I want you to come up with a fractional solution to vertices such that for every edge, I like U plus UV is at least weight of V. So like every edge has a weight, which is like, for example, if you have a cardinality, it is 1, so that you pick some weights on the vertices such that it is at least WE. Okay. Now I claim that you look at your potentials. Phi V, they form a feasible solution to dual. Okay. So how will I prove this? I will say that for each edge E equal to, say, UV, okay, for each edge E equal to UV, okay, it's dual constrained phi, its dual constraint is satisfied by phi. So let's call this vector phi. Okay. Now, so two regions. Okay. So first, let's see why this is true. So what does this algorithm does? Right? If weight of E is less than phi U plus phi V, then it discards this edge. Okay. Okay. So if an edge E is discarded, then what we know, phi U plus phi V is greater than or equal to weighting. So this is fine. Okay. If E is not discarded, so E is not discarded, then I claim after we put E in, after we put E in what you call a stack, it is satisfied. Okay. Why? Well, so let's say, what are you doing? So weight of E is basically, let's say, how do I say it? Okay, so let's say I would like to say, so this is my E, and suppose this is, so I have phi U old, phi V old. Okay, now I have phi U new, phi v new. And what is phi u new and phi v? We added something, right? So now let's see, what did you add to phi u and what did you add to phi v? Okay. So if you recall, what do we, so this is nothing but weight of E minus phi u plus phi v, like this is old, right? This is what it is, W tilde is. And phi u new is nothing but phi old of u plus W tilde of E. Phi v of new is phi old of v plus W tilde of E. Okay, so let's see what can we say. Weight of E is definitely less than equal to weight of E plus weight of E tilde, right? Now, what is weight of E? Well, weight of E is nothing but phi old of u plus phi old of v plus W E tilde, okay, plus W E tilde, right? Now, is this fine? Right? And now I take this into one and I take this into this. So what did this give me? Phi new of u plus phi new of v. Okay? So definitely, so what did we show? That, and since phi never decreases, like phi is a monotonically increasing, what is it? So what does this happen? Once an edge is satisfied by some phi, later phi might change, but phi can only increase, which implies that this phi will, like these edges will remain satisfied. Now, what does LP duality tells us? What does LP duality tells us? It tells us weight of M star, right? It's an integral solution, is less than equal to opt primal LP, right? Because if you relax, this is, and what we know, it is less than equal, it is equal to opt dual LP, right? Opt dual LP, at primal dual max and min. But it's a minimization thing, right? So it is less than equal to any feasible solution, right? So in particular, this is less than equal to summation V in V phi V, right? This is it. Now, so this kind of tells us that these potentials are potentials provides a kind of, so lower bound on, say, weight of M stars, right? So potential is, so if we are able to bound our matching in terms of these potentials properly, we will have a good something. Now, what we are going to do is make slight changes here, and I'm going to do, I will fix this epsilon, and I'm going to write 1 plus epsilon. Okay, so I look at any edge and I say, look, are you at most 1 plus epsilon time your potential? Then I move to the next stage. That's all the changes I will do. But now let's see what changes does this do to primal dual. Okay, now if an edge E is discarded, I'm going to show to you that this inequality here, now I cannot say this, but I have a weaker inequality. And what is this weaker inequality? So the weaker inequality will prove is weight of M star is less than equal to opt LP, that is still primal LP, this is perfectly clear, which is equal to opt dual LP, which is less than equal to 1 plus epsilon times summation V in V phi V. Okay, so I don't know whether phi V satisfies this property, but if I take each of phi V and multiply each of the element or each of the weight, each of the potential by 1 plus epsilon, then it starts to satisfy my inequality, right? Then it starts to become feasible solution. Or in other words, what are we saying is, so let's see, what I'm saying is phi V forms phi V, say not forms, scaled up to 1 plus epsilon forms a feasible dual solution. Okay. And why? Well, let's look at this. Okay. If edge E is discarded, why it is discarded? Because you know, in this case, 1 plus epsilon times phi U plus phi V, or weight of A is less than equal to this. So this is definitely satisfied. Okay. Now if I go here, I do whatever I did here, W prime and this and everything. But now, what do I know? I will still get the fact that, okay, so this is fine. I write this. This is old, this plus this. Now, is this fine? But this is also less than equal to 1 plus epsilon times phi nu U plus phi nu V, right? Nothing would change, right? If it is less than, if it is equal to this, then this is less than equal to 1 plus epsilon times this also. Okay. Now, what is happening in this algorithm is simply the following, that you should think of this, that at some point of time in our algorithm, when an edge comes and I say, look, what happens if I'm going to subtract, if all the edges which were incident to me subtracted a factor 1 plus epsilon times their weight from me, do I still become negative? If I become negative, then I will charge them for, making me negative and throw myself off. Okay, so that is all that is happening in this algorithm. Okay, now there are two things to consider. Okay, so we can also prove that this is a 2 into 1 plus epsilon approximation using primal dual, but we will not go there. This is just to give you intuition why this is being done, is because it gives us a handle on our potential. Okay, it gives us how good or bad our potential is with respect to weight of M star. Okay, but I will go back to my algorithm. Okay, and let me first prove to you that even with respect to this modified version, it's a factor 2 into 1 plus epsilon approximation. That's one. And secondly, why that we have modified with this 1 plus epsilon, now we have taken care of the fact that the stack will not grow too much. Okay, so these are the two things we have to understand. Okay, so question number 1, why is the modified algorithm 2 into 1 plus epsilon approximation? Okay, okay. Let me okay. So I'm going to define, and then we'll come to the question number 2, why we will not add too many edges. Okay. So I'm going to define for analysis. Okay. For analysis, a new weight function is the following. 1 plus epsilon if phi u plus phi v is less than equal to 8e, which is less than equal to 1 plus epsilon times phi u plus phi v. Okay? And weight of E otherwise. Okay? So this is my new weight function. Okay? Now, think of running the algorithm. Okay? Now, think of running the algorithm with new rule. Add to stack F if weight of E prime is more than phi u plus phi v. Okay? Now I claim to you this is equivalent to adding to S with rule weight of E is greater than equal to 1 plus epsilon times phi u plus phi v. Okay? Why? Well, that's very simple. Okay. So what we do, so I just check is, so I'm going to run this algorithm with respect to this W prime E. Okay. So so what is this W prime? Whenever an edge comes, okay, I compute W prime of that, okay, with respect to this weight function, okay, and like as I told you, we are not going to do this. This is just for the analysis purpose, okay. So then I add this, okay. Now what happens? So I want to say that this rule will add edges to the stack if and only if this happens. Well, this is true because suppose weight prime of E is greater than equal to phi u plus phi v. Now, but suppose weight of E is less than, but you added wrongly probably. Okay, it means, right? What does this imply in this case? Okay, so suppose this is this, but this is this, then in this case, what is a weight prime of E is equal to weight of E into 1 plus epsilon, right? This is the way we have defined our weight function. But then this is less than equal to phi u plus phi v, right? Now, but you started that weight prime of E is more than phi u plus phi v, so this cannot happen. So this rule and that rule are exactly the same, okay? Now, what have we shown with respect to this? That we have shown that with respect to this, we do have a factor 2 approximation. So what does it mean? It means that weight prime of M is at least weight prime of M star. Just 1 second. Okay, so what we know about this, it is weight prime of M star W prime divided by 2. Okay, this is what we know. So if M star is a maximum weight, like weight prime of M is at least weight prime of M star W prime divided by 2. Now let's see what we can say about okay. Now what we know about weight prime of any edge, it is less than equal to weight prime weight of E, but it is between this. Okay. Now weight of M, this is what we are interested in, is at least, is this fine? Weight of M is at least weight prime of M, because look at any edge. With respect to W prime, the edge weight can only decrease, it cannot increase. So this is perfectly fine. But now here it is. So what we know that this is W prime M W prime divided by 2, right? So what I mean by this is that, look, because of our algorithm, M is at least a factor 2 approximation with respect to maximum weight matching W prime. Okay. Now, I think I wrote something garbage here. Wait, forget for now. Okay. Okay. So I have a weight. Let M be the matching which is returned by algorithm. Now this is at least weight prime of M. Now because, right? So M is the matching which is returned by my W prime. Okay. So what I'm saying now, if I look at the weight function of that, M is this much. But what is the weight prime of M? Well, I know this is a factor half approximation or factor 2 approximation, however you want to say, with respect to the best matching here. Now, I claim that this is less than equal to weight of M star of W. What is M star of W? This is a max weight matching. This is with respect to W. What is this? This is a max weight matching with respect to W prime. Now, look, now this is some matching edges. Okay, I'm saying, look, this is with respect to W prime, this is the best weight you can hope for. MW star is some set of edges. Now let's sum the edges of those weights. With respect to W prime, this will be only smaller than the maximum weight matching, which is equal to 2. But now what we know about this, the relation between this, now look at any edge here. Any edge here is at least the corresponding edge with respect to W divided by 1 plus epsilon, which implies that this is less than equal to W MW star 2 into 1 plus epsilon. And we are done. Okay, any question? Okay, so look, we just modified this weight function, okay, for the analysis, and we said, look, even with respect to this new modified weight function, look at the we have this relation, but each edge is just 1 by 1 plus epsilon factor away in W prime and W, and that gives me a lower bound of 2 into 1 plus epsilon, and that's all that it is saying. Okay, now let's say what do you want to say? Okay, so the only thing which we didn't discuss yet, why does stack not grow? Why do you think stack does not grow? Okay, so to do that, what I will do, that I will focus on some vertex U. Okay, now let's ask ourselves, let's see, what do I want to say here? Okay, so let's see the changes. Okay, here it is, say V. Okay. So let's see the changes in phi in 2 iteration. So look at phi V, right? And in the next iteration, some edge has with respect to this. This is what happens. right? This is a change, right? Right. So phi v in each iteration changes by, in phi v, we add some weight of ei, where say ei equal to u comma v, right? So this is how, when you add a new edge, this is how phi changes. Okay. But what do you know about this residual weight? Remember, what was this? This is what was there. Now, what can I say about this? Well, this is greater than equal to phi v. And why did we go here? Because weight of ei is greater than equal to 1 plus epsilon times phi u plus phi v, right? This also we know. Then I can definitely say, if weight of ei is greater than equal to 1 plus epsilon times phi u plus phi v, then what is this quantity? So weight of this minus this is definitely at least epsilon times phi u plus phi v. Look, weight of ei is at least 1 plus epsilon times this. So if you just expand it, this minus phi u plus phi v is at least epsilon times this. But this will give you 1 plus epsilon times phi v. Okay. So now notice, look at the potential at phi v, right? Potential at phi v, what is the largest potential of? So every weight is polynomial, right? So the phi v can grow up to some poly in n. Okay, this is what phi v can grow. Okay, now each time, what is the potential? Potential grows geometrically. Geometrically by factor of 1 plus epsilon. Okay, by factor of 1 plus epsilon. So potential is growing geometrically by a factor of 1 plus epsilon. So somehow if we can show that phi v quickly becomes, or phi v quickly becomes 1 or even epsilon, we are good. Because once you become epsilon or something, very quickly, I mean, suppose if you quickly became 1, right? Or in the first step you became 1, okay? Then how many steps do you need to become poly in n? Well, all I care is 1 plus epsilon to the power x should be equal to, or like greater than equal to some n to the power c. So x is like roughly log 1 plus epsilon times n c, which is order log 1 plus epsilon times n. Okay. So, but it is not true that you become 1 immediately. So look, first time is very clear. So when you have an UV and both potentials are 0 to start with, phi u is equal to 0, phi v is equal to 0, then what is the first condition you do? Well, then, and if both are 0 and some edge has come, then what you know about this? Weight of E is more than equal to 1 plus epsilon times phi u plus phi v, right? Which is, yeah, so weight of, so if we assume that minimum weight is 1, greater than equal to 1, then this is fine, because the first time an edge has come, you know that it is at least 1 plus epsilon times 0, so it is more than 0, but it is at least 1. So now what is the potential will you be adding? Phi u, you will be adding weight of E, phi v, you will be adding weight of E. So this is great. But So if both u and v are 0, then this is fine. But the problem will happen. This is u, okay, and here you have added new way v. Okay, so now E is the first edge incident on V that is added. Okay, that is added to V. Now, all we know at this point of time that weight of E is greater than or equal to 1 plus epsilon times phi U plus phi V. But V is the first time, so it is 0. So this is actually equal, greater than or equal to 1 plus epsilon times phi U. Okay, this is all that we can say. Now, in this case, all we can show, I mean, if you work a little bit, so what do we need to show? We somehow need to show by how much, what is this quantity? 1 plus epsilon times phi U, right? This is what weight of E is. But what will be you adding? So the phi potential of V you will be adding is, what is the potential of V? We will be adding to this, it is 0. So weight of E minus phi of U. This is what you will be adding, right? And but in this case, somehow we need to show that, yeah, so this is what you will be adding. So somehow we need to show that it is, say, so look at weight of E minus phi of E. So this is like at least okay, which is phi of U, okay, no, which is greater than or equal to epsilon times phi U. Okay, so this is what you can actually show, and so if you, so you can show that this at least will add some function of epsilon in the base case, okay, and hence it will all become like we can show this is like so this number of edges that will be added is like some function of epsilon times log, okay, because you have got some quantity which is f of epsilon, and your every time after this you will be multiplying with factor 1 plus epsilon, 1 plus epsilon, 1 plus epsilon. So 1 plus epsilon times something into some f of epsilon should be greater than log nc. So if you do the normal maths, this should happen. So, but basically the idea is, I'm not going to do this calculation, but basically the idea is by introducing 1 plus epsilon, what we have made sure that we are not going to add edges arbitrarily when weights are this, but whenever we add weights to edges, my potential grows exponentially. So if we have polynomial weight, we will converge very quickly. Okay. Okay. So at least that was an idea. So let me quickly tell you another algorithm. Let's see if I will have just 30 minutes maybe or something. These are like, okay. I don't know whether you have seen. So let me do some auction algorithms. Okay. Okay. So I'm going to do a bipartite matching, and this time we are going to do a cardinality bipartite matching. Okay. So the algorithm is simple. Okay. So here I have bipartite graph, left, right. These are I'm going to call bidders. And this is I'm going to call items. Okay. Okay. What does edges show in the graph? Edges are like items a bidder is interested in. Okay. Okay. In the beginning, every bidder is unallocated. Okay. And every item has price 0. Okay. So in each round, what will I do? So I'm going to define an auction. So the auction happens as follows. In each round, okay, an arbitrary bidder, arbitrary unallocated bidder, not anybody, is selected. So you just select one of the arbitrary bidder, okay? Is selected to report an item he would like to have, so only his neighbors, with minimum price. Okay? Okay. So suppose I have a V and this is his neighbors. Okay. So he was unallocated. So he says, okay, what I will do now, I will do the following, report. Okay. So this guy, V, reports an item with minimum price. Right? So now why it is a bidding? Because he's willing to pay a little bit more. Okay. So what does he does? How does he bid? It increases the item price by some epsilon. Okay. And reallocates the bidder. Reallocates item to this bidder. Okay. And continue this process, but this is also called welfare minimization or welfare, what do you call? This has a very term, let me tell you what this term is. Welfare maximizing assignment. Okay, so why it is a welfare maximizing assignment, you will see in a minute. So look, you start with the item price 0, but price is capped at 1. Okay. Continue this process. While keeping the price of item at 1. So suppose I am a bidder and I reached 1. Okay, after that this item is like, it's mine. This item cannot be reallocated. Okay, that is, the item no longer can be reallocated. So is the algorithm clear? So think of this. So this is a bidder and this is item. So in the beginning, every bidder is unallocated. There's nothing, no assignment, and every item has some price. Okay. Now notice that in this process, every item is an integral. It means either I assign it to you or I assign it to someone else. I'm not going to assign it fractionally. Oh, take 30% of me, 40%. No, right? So at each item, I pick a bidder who has not been allocated any item. It looks at all its neighbors, picks at an item with a minimum price. Okay, so I mean, if it had been doing a general auction, then maybe this guy would have a priority which he likes, but nothing. He loves all his elements equally. Then this is the most basic dumb auction. Okay, so he picks up an item because look, he's a bidder. He wants to maximize his profit. So to maximize his profit, and he has say 1 unit of cost or $1 or whatever you want to say. This is what he can pay for, and he can buy an item in $1. That's all. So no item at any point of time can go beyond $1. Okay. So what he does, he looks at the current prices. He picks up an element with the cheapest price, and he says, "Look, I'm willing to pay for this, whatever its price is, plus epsilon." So this algorithm has also a running parameter epsilon. Okay. So then suppose I'm a person who's saying, okay, fine, you are ready to pay more to pay for this item. I give you this item and I increase this price. Okay. Okay. I keep going this process. Okay. But the moment someone reaches 1, then that item is allocated to that particular bidder. And notice that at that point of time, bidder has used up his $1 completely. So now he cannot buy any other item. Okay. So at any point of time, okay, what can you say about bidder and item assignment? What is this? This is a matching. Right? So there are 2 questions. What will happen when algorithm stops? Have you seen this algorithm before? Anybody? Okay. Notice that some bidder okay. So at every step, there's a bidder which is unallocated. He bids for an item, he gets allocated. So by virtue of the algorithm, I only allow a bidder which is unallocated to bid. Okay, so that is why at every step of my algorithm, I maintain that whatever bidder item assignment is, it's a matching. Okay, but now my question is, will this algorithm stop? Or what I mean, when I say will this algorithm stop, will this algorithm converge? Okay, and when it will converge, what kind of matching guarantee we can give? Okay, so this is well known from economics that converges in order n over epsilon round and produces 1 minus epsilon approximation to matching. Okay. So does it gives us a polynomial time algorithm to compute maximum size matching?
No.
No? Why, Piotr?
Well, it's just approximation.
Yeah, but epsilon is in your hand.
Oh, yeah. Okay, yeah.
So if I substitute epsilon equal to 1 over, say, n plus 1, right? Then I will probably go order n square round. That's fine. But at the end, what will I produce? I will produce matching of size, say mu g is the maximum size matching. I'm going to produce a matching whose size is at least this much, which is equal to mu g minus mu g by n plus 1. But this is less than equal to 1. So this is like, this implies that m is a maximum matching. So actually it's an alternate algorithm for maximum matching. Okay. Okay, so people in like streaming and distributed algorithm discovered this algorithm from some economics, which people have been using from 80s. Okay, but notice that for a fixed epsilon, you are getting a very close to an optimum approximation. Very close to an optimum approximation in like in small amount of time. Okay, so. Okay, so I just wanted to give you another algorithm, which is like, so why this algorithm is very interesting, because recently, I think I just read today, so, okay, SOSA 2021, they have showed that a modification of this Bidder algorithm, we will be able to find 1 minus epsilon approximation to maximum matching in order 1 over epsilon passes. Okay, 1 over epsilon square passes. Okay, so like it's a slightly different, like it is not at all obvious that it will stop in this much of round and it will produce you 1 minus epsilon approximation. Okay, so this is not obvious, but what is not even more obvious is that we can apply this algorithm. So for example, look, this algorithm is, if I would have just space bound, then this is very simple algorithm to maintain, right? What are you maintaining at this point of time? You are maintaining the current assignment, okay? Current assignment. Like, so suppose I maintain current assignment. So if I maintain my current assignment, I maintain my current pricing. Okay, and every time if epsilon is some constant, I'm increasing my price by factor epsilon. So it's not too much, like so I keep these prices. Okay, now what do I need to do? So in the next round, I have to do some reallocation with respect to some person who's unallocated. So what does he does in the next time? Like next time he reads the stream, and what he does is that, okay, he just bids for an item which has a minimum price now that he can see, okay, and update the prices, update the assignment. Okay, he's done. Next time when it comes, it can do this. And what is this lemma tells us, a theorem tells us that, well, if you do order n over epsilon rounds of reading, then you will get 1 minus epsilon times mu g, right? But what this paper is telling us, that there is a clever implementation of this, that I don't need order n over epsilon rounds. I can do it in order 1 over epsilon square rounds. Okay, so that is a bit clever implementation of this algorithm. So there, we will not be doing one step at a time, but several steps glued together at a time. Okay, and then we will show this is good enough, and we will converge much more quickly. So basically, what this tells us is that, forget about this, is that it tells us that there is a way to implement this algorithm, okay, that it will converges much more quickly than order n over epsilon rounds, okay, and give us a good algorithm. But amount of objects we need to store, about amount of time we need to do all these things will depend. Okay, so so for the plan for the next week is that I will tell you a highlight of this algorithm, and then we will do parameterized streaming. Okay, so this is the plan for the next week. Okay, okay. So I think I was a bit more slower than I thought, but fine. Okay. I think I should stop. It's already 1.5 hours. Okay. Okay. Then, if anybody has a question, else I will stop for the day. No question? Okay, then see you on Monday.